Hello, it's Mr. Doro. Today we're going to be talking about pH calculations and other related calculations that go along with pH. By the end of this, I'm hoping you'll be able to define pH, explain what the pH scale is, and calculate pH and other properties that are related to it. The first thing we have to talk about when we're talking about pH is the self-ionization of water, also called the auto-ionization of water. So I've got a beaker right down here that's got all kinds of water in it. This is all water in here. Billions and billions of molecules. And so what will happen is every once in a while, two of these water molecules will interact with each other, actually react with each other, and become like a Bronsted-Lowry acid and base, and produce hydroxide ions and hydronium ions. Now that doesn't happen very often, but every once in a while in here this will happen, and then the reaction will go back. It's a reversible reaction to make the water molecules also. Now when I said it doesn't happen very often, the concentration of these hydronium, H3O+, and by the way, when you put brackets around it like that, that means concentration, which is molarity, is 0.0000001 molar, which is 1 times 10 to the -7th molar for the H3O+. Now notice this, for each H3O+ that we're making, it also makes a hydroxide ion. So the concentration of the hydroxide ions is also going to be the exact same. OH minus equals 1 times 10 to the -7th molar. So when you're drinking water, you are drinking some ions, but most of it is just pure water because only 1 times 10 to the -7th moles per liter would be these ions that are in here. So it's important to know that in pure water, the concentration of H3O+, hydronium ion concentration, is going to be equal to the concentration of the hydroxide ions, OH minus. And so you want to make sure that you have that in your notes. H3O+ equals the concentration of OH minus. Now you can change this by adding, if you add an acid to this, remember acids make these hydronium ions, the H3O+, and so that is going to increase this amount. But in pure water, they're going to be equal to each other. So what really makes a solution neutral, acidic, or basic is a comparison of the concentration of the hydronium ions to the hydroxide ions. In pure water, when you have the equal amount of hydronium and hydroxide, that would be considered neutral. But if you were to add acid to this pure water, we started with pure water and we added an acid, and now we're increasing the hydronium ion concentration when we do that. When we increase the hydronium ion concentration, the hydroxide ion concentration decreases. And so that gives us an overload of the hydronium ion concentration. So for an acid, we're going to have the hydronium ion concentration is greater than the hydroxide ion concentration. That's what makes it acidic. And if we were to add base to pure water, and I'll have the base be this green color right here, then that would be increase in the hydroxide ion concentration of that pure water, and therefore decrease in the hydronium ion concentration. So as basic, we still have hydronium ions, but we have a greater amount of hydroxide ions. And that makes it basic. These definitions you want to write down. So here are 3 different situations of hydronium and hydroxide ion concentrations, and I'd like you to figure out which one is if there are any that are neutral, acidic, or basic. Here's what you have to do. You have to compare your hydronium ion concentration to your hydroxide ion concentration. This can be a little bit tricky sometimes because of this negative exponent in the scientific notation. Remember, this really means 1.0000 10 zeros and then the 1. So this decimal right here would move over 11 places here. This decimal would move over 3 places, which is going to make this one the greater number. Even though this 11 is a greater number, it's a -11. This is -3. And so this is going to be a greater hydroxide ion concentration, which would make this one basic. You pause it for a second and try to figure out what the next two are. Okay, hopefully you really paused it, because this is something you need to test yourself on. we're not really looking at these first numbers right here. You might look at the first numbers and say, oh, this is the bigger number, 4.3. But this is times 10 to the negative 12th. So this decimal moves 12 places over this way. This decimal only moves 3 places over this way. So that's going to make this one the greater of the two. And so this is going to be acidic. And finally, this last one right here, this decimal would move 6 places over this way. This one will move 9 places over this way, making this one the greater. This is the OH I listed first this time, and so that would make this a basic solution. Now that brings us to the question, how do we calculate the hydronium and hydroxide ion concentration? Well, we're going to use an ion dissociation constant for water, which is called Kw. This is the formula to find Kw. Kw equals the hydronium ion concentration times the hydroxide ion concentration. So if you're given either one of these, if we know this constant, since it's a constant, it'll be the same every time, then we can solve for the other one. Now for pure water, we found out on the other page that the auto dissociation, it will automatically make a concentration of hydronium ions of 1 times 10 to the negative 7th and hydroxide of 1 times 10 to the negative 7th. When we multiply those two together, we end up with 1 times 10 to the negative 14th. And this is our Kw. Any solution dissolved in water is going to have this constant for the ionization, and we're going to want to put a star next to that one also, along with that one up top, so we can use this Kw each time to find whichever concentration we weren't given in the original problem. Now we can use this formula if we're given one of these concentrations to find the other one. So in letter A right here, it gives you a hydronium ion concentration of 2.4 times 10 to the minus third molar. Wants to know the hydroxide ion concentration. So we're going to use this formula, Kw equals hydronium ion concentration times hydroxide ion concentration. We know what Kw is. It's 1 times 10 to the negative 14th. We know what H3O plus is. So now we just have to solve for OH. And so in order to get OH by itself, we do Kw divided by this H3O plus. And so I'd like you to plug these all in right here. And so we get 1 times 10 to the negative 14th equals 2.4 times 10 to the negative third, molar that is, and then times OH minus. So I take this 1 times 10 to the negative 14th. Remember how you plug it in your calculator. This is 1 EE negative 14 divided by 2.4 EE negative 3, and you should end up with this answer of OH minus concentration equals 4.2, that's in 2 sig figs, times 10 to the minus 12th. Since this is concentration, the units will be molar or molarity, and you have your answer for hydroxide ion concentration. Now I want you to try to solve this next one. It gives you the hydroxide ion concentration. Pause it and try to find the hydronium ion concentration. Okay, and I got 1.6 times 10 to the minus 10th molar for that. If you're not pausing it and trying to do these, then really you're not helping yourself. You're just going through the motions. So make sure that you're trying to work through this. It's going to help you in the long run, I promise. I want to quickly show you this pH scale, and as the pH you see increases, the number for the pH, you can see that the hydrogen ion concentration actually decreases. It's getting smaller and smaller, but the hydroxide ion concentration increases, and you can see that these have an inverse relationship with each other. You can also see a little relationship with the number for the exponent for the hydrogen ion concentration and for the pH value. Once we know the concentration of the hydronium ion or the hydroxide ion, we can then calculate the pH, or something that you're not very familiar with, something called the pOH. Normally we're using the pH, but we're going to learn how to calculate this also. So when we know the hydronium ion concentration from our Kw formula that we did before, then we can just plug it into this equation, which is negative log of H3O plus. Now, log is a button that's on your calculator, and so all you got to do is hit, depending on what kind of calculator you have, if you have one that has the display as you punch it in, you see what you're punching in, then you would just hit negative log of that number. If you don't have a calculator that shows that display, you might have to hit the number and then hit log and then hit negative on it. So I'm going to give you a hydronium ion concentration for you to practice. So here's a problem over here on the side. concentration of hydronium ion, which also could be H+, they can mean the same thing, remember they're interchangeable, is 2.61 times 10 to the minus third. So you just plug it in, negative log of 2.61 times 10 to the minus third. And the answer that I got on my calculator was pH equals, I got 2.583359493. Now sig figs are a little bit weird for pH. Here's what you got to know. This whole number does not count. The number before the decimal does not count for sig figs. And so this had 3 sig figs up here, 2.61. And so those 3 sig figs come after the decimal on there. So this is going to be really 2.583 for the pH on this. I'm not going to be terribly picky on the sig figs, but that's the correct way to do it. We can also then calculate the pOH very easily by just using this formula right down here. pOH and pH together are going to equal 14. So if I want to find the pOH of this one, pOH would just be 14 minus the pH. And so when I do 14 minus 2.583, then I'm going to get the pOH to be 11.417. So that's my pOH. Whoops. Now, if you were given the concentration of OH, you could easily find the pOH by doing negative log of OH, and then find the pH the other way. And these are interchangeable back and forth. Why don't you go ahead and do yourself a favor and try this one out. I'll give you the concentration of OH minus, and that's the concentration. Find the pH and find the pOH. Pause it and try that one out. So here are the answers to those. These are the basic parts of these calculations. We're going to get deeper on these, but you have to have these basics down first. So if you're not getting these, then you need to talk to me about it. Now, if we're given one of these four, pH, pOH, H3O+, or OH-, we can find all of the other three. And so there is one other little trick to it, and that's if you're given the pH, then go into those concentrations. But I'm going to show you how to do that right now. So if you're given the pH, 1.26, and you're asked to find all three of these other ones right here, then here's what we're going to do. We're going to start with the easy one. The easy one is to find the pOH, because remember, if we just do 14 minus the pH, 1.26, that's going to give us the pOH, and that is going to be 12.74 equals the pOH. So that was an easy one. We got that taken care of. It gets a little bit tougher when we want to find the H3O+ and the OH-, because we have to use something called the inverse log. Remember, our formula is pH equals negative log of H3O+. We know what the pH is. Our pH is 1.26. And then it's the negative log of H3O+. So now on your calculator, I want you to find probably right with the log button, maybe right above it or below it on the button part of it, there's a little button that says 10 to the x. That is anti-log. And so what you need to do then is you need to plug it in your calculator like this. 10 to the x, you hit that button, and then you have to hit the negative, because we're going to use this negative part right here from the formula. So you're going to have to hit the negative 1.26. That is, since that was the pH and we're finding now the H3O+, when we hit that, we're going to end up with 0.05495, which in the correct number of sig figs is 5.5 times 10 to the minus 2, and that is my hydronium ion concentration. Now I want you to plug that in, because if you don't hit this negative right here, then you're going to end up with 18.2, and that's definitely going to be wrong. So now we have the hydronium ion concentration. We can find the hydroxide ion concentration either by doing this same formula with the pOH, or we can do our Kw equals H3O+ times OH-, and so that's the way I'm going to do it. Now I've squeezed a whole lot in here, but you can see on the bottom I did this. Kw equals H3O+ times OH-. Kw is this. This is my H3O+. I solved for OH-, and I got 1.8 times 10 to the negative 13th. I put boxes around all three of these right here. And also, to check my answers, when they're not exactly 1 right here, these two little times 10 to the negatives here should equal negative 15 if I did it right. And they do in this case. So here's one problem that I'd like you to do. And remember, this is just a springboard to the next stuff that we do, and so if you get this down pretty well, then you're going to be in good shape. I'm not going to give you all the answers to this, but I will give you one. I'll give you the pH. If you get all these right, then you're going to end up with the 10.61 pH. So, hope you do well. Go back and look at how to do these problems if you need to. Have a nice night.